Good evening, everybody. This is Math 2414. It's March the 7th. A couple of announcements to make here at the beginning, like always. There will be homework due on Sunday this week on March the 11th, so be prepared for that. I did assign a couple of problems on Monday's lecture, and I will assign I'll assign 2 problems today also. So you'll have 4 problems to turn in on Sunday this week, or by Sunday, I should say. Your exam 2 review, it says it's uploaded. It's not exactly, this is currently 7 p.m. Wednesday night. So as of right now, it's not uploaded, but it should be uploaded before the end of the evening tonight because I have it done, so it just hasn't been uploaded yet. So the exam 2 review should be going up soon. Remember that the exam 2 testing window is March 22nd through the 27th. So, it opens up 2 weeks from tomorrow. So, it's getting pretty close, certainly. Spring break is next week. So remember, no lectures next week, no office hours next week, no online office hours. Let me write that down here also. But if you do want to meet with me sometime in my WebEx room next week, then what I want you to do is email me probably the day before, or maybe 2 days before you think you might want to meet, and we'll see if we can come up with a mutually agreeable time. Don't try to email me now. Don't try to email me today or tomorrow. It's probably a little bit too soon. But, within a day or two of when you think you might want to get together, email me and we will see what we can work out. I will be checking email probably at least twice a day next week. On campus hours, I will be on campus for office hours March 21st and March 22nd. The 21st, 4 to 6 p.m., the 22nd, 9 to 11 a.m. I have question marks by both of those. It's not 100% set in stone that those are going to be the times, but probably those are going to be the times. That's the times that I met last time I was on campus. So, all right, so be keeping up with the material. Please let me know if you have questions. I'll be happy to help you out. All right, today we are going to continue talking about parametric equations. Last time we introduced how to represent a graph parametrically, talked about some basic things having to do with parametric equations. Today we're going to center on parametric equations in calculus. And in particular, we're going to be talking about how to find the derivative of y with respect to x if x and y are defined parametrically, how to find the second derivative of y with respect to x, find the slope of a tangent line, vertical and horizontal tangent lines, and then hopefully we'll also get into arc length and surface area. Just to a little bit of a note right here, this material right here will be on exam 2. Arc length and surface area parametrically, that's where exam 3 is going to start. So I'm going to shut down the material that's on exam 2 with today's kind of about 2/3 of the way through today's lecture. Okay, so let's get started. Let's jump into this. Let's say that we've got that x and y are defined parametrically in terms of some parameter t. So x is f of t and y is g of t. All right. Now, so you can get a graph from that. We've talked about how that was most of last time's lecture, was about obtaining a graph from that parametric form. And so now what we want to do is talk about slopes of tangent lines on a graph like that. So in other words, we want to look at dy dx. So dy dx, we define to be dy dt divided by dx dt. It's a pretty simple way of calculating the derivative of y with respect to x. It's dy dt divided by dx dt. And the second derivative of y with respect to x, now this will take a little bit of writing out to do this. So the second derivative of y with respect to x, remember that is simply, that notation I just used right there is simply shorthand for the derivative with respect to x of dy dx, like that. Right? That's just a shorthand for that. And that form, really, you could write this way, even though you don't typically see it this way, you could write it this way, that it's d dy dx, dx, like that, that the variable you're taking the derivative of is dy dx right there. And then if you simply use how we define the derivative right above, notice the derivative above tells you to take the derivative, when you've got, let me write this off to the side here, when you've got dy dx right here, this is telling you take this variable and take its derivative with respect to t, and then take this variable and take its derivative with respect to t, like that. Right? And so that's exactly what we do, but the derivative, the variable in the numerator is not y in this case, it's dy dx. It's still the same process. You take the derivative with respect to t of dy dx, and you divide that by the derivative of x with respect to t. And that little notation right there is how we calculate the second derivative of y with respect to x. So the second derivative of y with respect to x is the derivative with respect to t of dy dx, and then that's divided by dx dt. Okay, so that's how we calculate the second derivative right there. And this is how we calculate the first derivative right here. Okay, so let's, with that in mind then, let's jump right into an example of that and have a look at how that would work for actual functions. So let's say we have x is t squared plus 5t plus 4, and y is defined to be 4t. So x and y are defined parametrically, right? And so, and the directions here would be find the slope and the concavity when t is equal to 0. Okay? So now notice that you're given the value of the parameter, that t is equal to 0, but you certainly don't know the point that you're talking about. So the point, in case you need this, you can calculate the point, right? If t is equal to 0, then what do you know? That x would be equal to, from our parametric equations, would be 0 squared plus 5 times 0 plus 4, and y would just be 4 times 0. So the point we're talking about, the parameter value is t equals 0. The point we're talking about in this case would be the point 4, 0. And depending on the problem, you might need that point. So make sure that you know what you need in the problem, whether you need the value of the parameter or whether you need the point in particular. All right, so now let's go ahead and find the slope. So we find dy dx for this problem. So dy dx is defined to be dy dt divided by dx dt. Right, so the derivative of y with respect to t is 4. That's simple. And the derivative of x with respect to t would be 2t plus 5. You're just differentiating those two equations at the top with respect to t. All right, and then notice that dy dx is given as a function of t here. So we use the parameter value to calculate the slope of the tangent line. We put 0 in here, and we get 4/5. So the slope of the tangent when t is equal to 0 is m equals 4/5. All right, and then we calculate the second derivative. So the second derivative of y with respect to x, so this is going to give us the concavity, is the derivative with respect to t of the derivative. So that's 4 over 2t plus 5, like that. And then that would be divided by dx dt, but we already have dx dt. That's 2t plus 5. Okay, so now it remains for us to find the derivative of 4 over 2t plus 5. Now remember that 4 over 2t plus 5 is really 4 times 2t plus 5 to the negative 1. So if you're calculating the derivative of that expression using the power rule, it would be negative 4 times 2t plus 5 to the negative 2 times 2, right, using the chain rule. And so that's what we have here in the numerator. This is going to be negative 4 times 2t plus 5 to the negative 2 times 2, and that would all be over 2t plus 5. And cleaning that up a little bit, you'd have that this is negative 8 over 2t plus 5 squared all over 2t plus 5. Or finally, negative 8 over 2t plus 5 cubed. Right? And that's the value of the second derivative. So then the concavity, you could look at the concavity. You could take the second derivative and evaluate it when t is 0. So you get negative 8 over 125. So that means that the function at this point, the graph, when t is 0, at the point 4 0, would be concave down because the second derivative is negative, but pretty shallow too because the concavities are really, its absolute value is really small. 8 over 125 is really close to 0. So there's a bend in the graph there, but it ain't a very big bend in the graph at all. All right, so there's an example where we calculated derivative, second derivative there. All right, so let's move on to a second example here. Okay, so this example, we're given that x is equal to 3t minus t squared, and y is equal to 2t to the 3 halves, like that. And what we want to do is we want to find the equation of the tangent line, find the equation of the tangent line when t is equal to 1/4. All right, we want to find it when t is equal to 1/4. Okay, so if you wanted to find the point, right, you would take the two equations that you have, and you would certainly, you'd substitute 1/4 in. So you have, so might as well find this point now. So x of 1/4 would be 3 times 1/4 minus 1/4 quantity squared, like that. And so that would be 3/4 minus 1/16. So that would be 12/16 minus 1/16, or 11/16. So that's our x value. And then the y value, this would be y of 1/4. So this would be 2 times 1/4 to the 3 halves. So that's the square root of 1/4, which is 1/2, cubed, which is 1/8, times 2, which would be 1/4. So you have 2 times 1/8, and this would be equal to 1/4. So when t is equal to 1/4 in this graph, you're talking about the point 11/16, 1/4. Right, those are the coordinates of the point when t is equal to 1/4 here. All right, so now we want to try to find the equation of the tangent line. If we're trying to find the equation of the tangent line, we need that point we just found. And so now we also have to find the slope of the tangent. So the slope of the tangent means, obviously, calculating the derivative. So we have dy dx is equal to, remember, dy dt divided by dx dt. The derivative of y with respect to t divided by the derivative of x with respect to t. So the derivative of y with respect to t would be 3t to the 1/2, just a power rule problem. And that would be divided by the derivative of x with respect to t, which would be 3 minus 2t, like that. And there would be our derivative. Pretty easy calculation right there. So now we take the derivative. We want to find the slope of the tangent line. So we evaluate this when t is 1/4. So in the numerator, you have 3 times 1/4 to the 1/2 power. And in the denominator, you have 3 minus 2 times 1/4. Like that. So 1/4, let's see, the square root of 1/4 is 1/2. Times 3 would be 3/2. So you have 3/2 right there. And in the denominator, you've got 3 minus 1/2. So that would be 5/2. Like that, because it'd be 6/2 minus 1/2. So 3/2 divided by 5/2, the 2's divide out, and you end up with 3/5. And so that is the slope of the tangent. All right, and so then we're ready to write out the equation of the tangent line. So don't forget with the equation of the tangent line, let's see, equation of tangent line. All we're doing is using the point slope form. That's the way I'll write it out. Y minus y1 equals m times x minus x1. We've got the point and we've got the slope. So this would be, let's see, would it be y minus 1/4 equals 3/5 times x minus 11/16. Not the nicest arithmetic in the world, but it's not bad. So you have y minus 1/4 equals 3/5 x minus, and let's see, that would be 33/80. Okay, that's nice. And then I would usually want you to write this in slope-intercept form. So this would be 3/5 x minus 33/80. Oh my gosh, some of you, your fraction arithmetic is horrible. Some of you just don't have any patience right here, and then you make a careless mistake in the fraction arithmetic. So you have 33/80 plus, and then this would be 20/80 right here. And so you end up with y equals 3/5 x minus 13/80. Right, and that would be our equation. Now that's the equation of the tangent line in rectangular form. So this is the equation of the tangent in rectangular form. And it's possible that you might want to write the equation in parametric form. So in parametric form, this gives us good practice for that. So in parametric form, the equation of the tangent, let's see, so let's first of all write down the forms that we wrote down in lecture last time for a line. And if you recall, we wrote x equals x1 plus x2 minus x1t, and y is equal to y1 plus y2 minus y1t, right? That's the general form that you could write. There's other ways you could do parametric equations for a line. This is just one way to write it. And so let's see, what would we have here? We'd have x equals x1, which would be 11/16. And then x2 minus x1, that's just, remember, that's just the denominator of the slope. And so this would be plus 5t right here. And then y would be equal to 1/4. And then the coefficient of the t for the y equation would be the numerator of the slope, which would be 3. And so there you have x equals 11/16 plus 5t, y equals 1/4 plus 3t. And that would be the equation of the tangent line parametrically. So the equation of the tangent line written parametrically. Now remember, you could always check that out. You know, does that set of parametric equations actually go through the point that you've got? You know, the point was 11/16, 1/4. So you could certainly check that out. And when t is 0, you get 11/16 and 1/4. It certainly goes through the right point. And it certainly has the slope because the coefficients of the t's work out like they're supposed to. So, okay, so there's a kind of bringing a few things together that we've talked about. So now as we talk about calculating derivatives at various points and everything. What, if you think back to when you're in Cal 1, after you started calculating slopes of tangents and everything, the next thing to do was to start looking at where you had vertical and horizontal tangents. And so let's talk about that for a few minutes and look at some problems where we've got vertical, or where we're trying to find vertical and horizontal tangent lines to graphs that are defined parametrically. So vertical and horizontal tangents, all right? So you could, there's several ways that this could kind of happen. First of all, if you've got, let's look at vertical tangents for a minute. All right, so vertical tangents, you've got, let's see, so if you have a graph, let's say, that looks like this, let's say you have a point right here, and you've got a graph, and remember, when we're talking parametrically, if a curve is defined parametrically, it has an orientation. So that's a point right there that has a vertical tangent right there at that point. So let's say that that's when t is equal to a right there. So what's going on at that point as the curve slices through that point, right? It's got a vertical tangent, there's no question about that. But let's look at the derivatives there. So the derivative of y with respect to t at that point, so the derivative of y with respect to t when t is equal to a would be positive in this case, because what's happening there as you go through that point, the y value is increasing as you pass through that point. So that derivative would have to be greater than 0. And then what would be true about the derivative of x with respect to t at t is equal to a? Well, in that case, there is no change. At that point, there is no change in the x value, and so that would actually be equal to 0. And so notice you're getting a vertical tangent line when dx dt is 0 and dy dt is some positive constant. And if you think about it, you could have the same situation, or a similar situation, I guess, but now, so here's our a point where there's a vertical tangent right there, but now let's change the orientation, right? The orientation now looks like this on the graph. And let's say that that's also at the point t is equal to a, right there. So now what do we have for that vertical tangent line? And let's actually draw a vertical tangent in both cases to kind of emphasize that that's what we're doing, is we're looking at where there's vertical tangents to these graphs. Right, so what's happening at that point with these two derivatives? The derivative of y with respect to t at t is equal to a. In this case, the y value is getting smaller because the graph is passing through that point, and the y value, the graph's going down at that point. So the y value is getting smaller, and so the derivative of y with respect to t would be less than 0. It would be some negative number here. And then what about the derivative of x with respect to t at t is equal to a? Well, that would still be 0 because at that point there's still no change in x. So, what have we got here clearly is that you've got vertical tangents, and don't forget how dy dx is defined. Dy dx is defined to be dy dt divided by dx dt. And so what are we saying here is that you've got vertical tangents at what value? Vertical tangent at t equals a when, what's true? The derivative of x with respect to t at t equals a is 0, and the derivative of y with respect to t at t is equal to a is not 0, right? It's either positive or negative, but it's not 0. That makes sense if you look at the way the derivative of y with respect to x is defined. What's dx dt? It's just the denominator. So you're saying when is that fraction that is the definition for dy dx. When is it undefined? Well, it's undefined when the denominator is 0. So that actually definitely makes sense there. Now, when you have, there's another way to get a vertical tangent line at a point, and another way to get a vertical tangent line is if the graph has a cusp. Don't forget cusps from back in Cal 1. I don't even think we've talked about a cusp so far this semester. So you might have a graph that looks like this, and let's say the orientation of the graph looks like I've got it drawn right here. We had a cusp in the cycloid that we looked at on Monday. That graph had cusps every time the graph came down to the x-axis. So this graph has a vertical tangent line there at that cusp also. Right, so there's this vertical tangent line passing through that point. And well, let's say that that's t is equal to a. There. Now, what's certainly going to be true there is that at that point, the change in x has stopped right there. And so we definitely have the same idea that dx dt when t is equal to a is 0. But what might happen here is that it's possible that the derivative of y with respect to t is also 0. Now, it may not be the case, but it could be 0 at that particular point. And I'm just going to put possible right there. All right, so this is a situation where with a cusp frequently is when you've got both derivatives being equal to 0 there. But if you think about it, we no longer are restricted to drawing graphs that pass the vertical line test. So what if you have a cusp that looks like this? Probably not the best picture in the world. Whoops. And let's say that that's the orientation of the curve right there. So what does that graph have at that cusp? Well, that now has a horizontal tangent line like that, right? And so that horizontal tangent line, what's going to be true there? Well, certainly it's going to be true that at that point that the y value briefly stops changing. And so it makes sense that dy dt is equal to 0 right there, that t is equal to a. But dx dt, it's definitely possible in a shape like this that at t equals a, this is equal to 0 also. This is possible right here. So notice what we're saying basically with these last two pictures is if both derivatives are 0, then you're going to have to draw the picture. Right, so both dx dt and dy dt is equal to 0. Then you have to look at the graph to decide whether you have a vertical or a horizontal tangent. Now, and then obviously there's one picture we did not draw here, but this is the most obvious case. This is for horizontal tangents. And so that's just your typical old graph that looks like this, right? Let's say that that's the orientation of the graph. It doesn't really matter. And at t equals a, this graph has a horizontal tangent, right? Has a horizontal tangent sitting right here at t is equal to a. And so at that point, what's going on? You've got what's true, that dy dt at t is equal to a is 0. And the way I've got that orientation drawn, dx dt at t equals a is positive. It's greater than 0. And then what could happen? You could also have a similar kind of graph, but now the orientation is backwards from what I've just drawn. And so there where you have a horizontal tangent, like that, same basic situation, right? What do you have? That the dy dt is equal, at t equals a, is equal to 0. And in this case, dx dt would be, at t equals a, would be negative, right? Because the x value, the graph's moving back towards the left, and so the x value is getting smaller. Okay, so to summarize, and we just try to draw a lot of pictures here. I don't want to confuse the issue too much here. So, you know, if you've got that x is some function of t and y is some other function of t, like this, then what you have is, if you have that, and then let's also write the definition of the derivative down while we're talking about this, right? That dy dx is equal to dy dt divided by dx dt. Then what we have here is that if you have dy dt is equal to 0 and dx dt is not equal to 0, then you have horizontal tangents. All right, if you have the dx dt is 0 and dy dt is not 0, right? So now the denominator of that derivative is 0. Then you have vertical tangents. And finally, if you have the dy dt is equal to 0 and dx dt is equal to 0, then you need to look at the graph to see what is happening. All right. So we're now going to look at some examples. This is something I would expect that you should be able to do, is you should be able to find horizontal and vertical tangents for a graph. All right, so I have several examples I want to work through here. So example, let's say I've got this set of parametric equations that x is equal to 3t minus t squared and y is equal to 2t to the 3 halves. And what I want to do is I want to find all points that have a vertical tangent. Right, so a vertical tangent is what we're after here. So what have we got here? Let's first of all look at the derivative. Dy dx we know is dy dt divided by dx dt. So dy dt would be 3t to the 1/2. dx dt would be 3 minus 2t. All right, a vertical tangent is what we're asked to find in this problem. So with vertical tangents, what are we looking for? We're looking for where dx dt is 0, and technically where dy dt is not 0. So dx dt is going to be 3 minus 2t. So you have 3 minus 2t equals 0, which gives you t equals 3 halves. Right, and then you could certainly verify that dy dt is certainly not equal to 0 at 3 halves. There's no question about that. All right, and so at t equals 3 halves, you have a vertical tangent. So what is the point? Right, at what point does this happen? So at what point is there a vertical tangent? I don't have the point. Right, I have a parameter value. Okay, so the point, what do? You just take the original equation and you substitute the original equations, I should say, and substitute 3 halves into both of those equations. So in the first one, this would be 3 times 3 halves minus 3 halves squared. So that's 9 halves minus 9 fourths, or 18 fourths minus 9 fourths, which is 9 fourths. And y of 3 halves would be 2 times 3 halves to the 3 halves power. So, you know, there's a couple ways you could do that, but you could say that that's 3 halves cubed is 27 over 8. So this is 27 over 8 to the 1/2 power. In other words, the square root of 27 over 8. Right, so this is 2 times the square root of 27 over 8, if you want to write it that way. And let's see, the square root of 27 is 3 times the square root of 3, and the square root of 8 is 2 times the square root of 2. And then the 2's would divide out right there. And so you get y to be 3 square root of 3 over the square root of 2. And you know that in a textbook, they will always rationalize this. I would definitely not penalize you for not rationalizing it, but you usually see it rationalized. So you have 3 square root of 6 over 2. Okay, so that's the point where there's a vertical tangent. And the point would be at 9/4 and then 3 square root of 6 over 2. 9/4 is exactly 2.25, and then 3 square root of 6 over 2 is approximately 3.67. 3 2/3. Okay, so that's just an approximation. Absolutely, definitely never a bad idea in a problem like this, when you're talking, especially when you're talking about vertical and horizontal tangents, to go ahead and make a sketch of the graph, or to use your calculator and get a sketch of the graph and make sure that it makes sense. So let's see, let's go ahead and enter this set of parametric equations here in the app that I've got. So I've got 3t minus t squared for x's. For y's, I've got 2t to the 3 halves. 2t raised to the 1.5 power. All right, and I've got it set up right now where the parameter value goes from -10 to 10. I'm going to change the color so we can actually kind of see it. And so we get a graph that looks like this one right here. And so what we would want to do is we'd want to say, hey, does this make sense in the context of our problem? In that, are we getting a tangent line that's at the correct point, or at a point that makes sense? So I'm going to go ahead and save that to my photo library and paste that in here. Make this smaller. I don't need a huge graph here at all. So I'm going to say that that's my graph. And notice you got 2.25, 3.67, and that would be this point right here. And that does make sense, right? That would be a vertical tangent right there at that point. And it certainly agrees. And so this, we feel confident that we've got the right answer right here. I think that's always a good thing to try to do, is to make a quick sketch of the graph. All right. So we found a vertical tangent line for that, or vertical points where there were vertical tangents on that one, on that graph. So let's go on to another example. And let's find both vertical and horizontal tangents for this one. So we have x to be t squared minus t plus 2, and y is t cubed minus 3t. So the directions: find all points where there are vertical or horizontal tangents. All right, and again, the emphasis here is on the word points. Since it's a point, we are going to have to find the actual x and y values, right? We're going to have to find the ordered pair. Okay, so let's do vertical tangents over here. So vertical tangents. So we know that the vertical tangents are when dx dt is 0. All right, so in our problem, dx dt would be 2t minus 1. Easy enough. You set that equal to 0. So you have 2t minus 1 equals 0. and that gives you t is equal to 1/2. And then you can find the point. Easy enough, just substituting that value in. So x of 1/2 and y of 1/2. So x of 1/2 would be 1/2 quantity squared minus 1/2 plus 2. And if you do the arithmetic there, that gives you 7/4. And y of 1/2 would be 1/2 cubed minus 3 times 1/2. Just plugging numbers in is all you're doing there. And if you do the arithmetic there, you get negative 11/8. So our point for the vertical tangent is at 7/4, negative 11/8. Right? Or if you're trying to identify it on a graph, that'd be 1.75 and negative 1 and 3/8, so negative 1.375. Right? If you're trying to locate it on a graph, it's easier to write it as a decimal. That's fine to do that. All right, horizontal tangents. Let's have a look there. So horizontal tangents, we know that dy dt has got to be 0 and not dx dt. So dy dt is 3t squared minus 3. Right, and if you want to, depending on how you write this out, you could factor and go this route, or you could use the square root method, however you want to do that. And so when you set that equal to 0, so there's dy dt right there. And when you set dy dt equals 0, you get t equals negative 1 and t equals positive 1. Okay, so when t is equal to negative 1, going to the original equation, you get x to be 4. Just substituting into the original equations, remember, just plugging in t equals negative 1, and y equals 2. And then when t is equal to positive 1, so evidently we have two horizontal tangents, 2 points where there's a horizontal tangent, you get x to be 2 and y to be negative 2. So you have 2 points where there are horizontal tangents, one at 4, 2, and then one at 2, negative 2. And then definitely, no question about it, on a problem like this, make a sketch of the graph. If you've got a calculator, use it to your advantage, is what I would definitely do. No question about that. So let's see. X is t squared minus t plus 2. Y is t cubed minus 3t. T cubed minus 3t. And I think the parameter values are probably okay like that. Okay, wow, this is a crazy graph. This looks cool. And I definitely want to go ahead and save that one. And let's go ahead and pull that one into this graph right here, or into this page, this screen right here. And let's see if this actually makes sense right here. I can actually position this right about in here to make it slightly bigger. I'll go ahead and paste it in. Okay, so we have a vertical tangent, and I'm getting that the vertical tangent is at about about 1.75 and about negative 1.375. And so that vertical tangent is right about in here. And that certainly seems to be an appropriate point. You've got the scale in there. If you're paying attention to the scale and counting the little tick marks, certainly not all the way over at x equals 2 and not all the way down at y equals negative 2. So that looks perfect right in there. So that vertical tangent fits in really well. And then, so the vertical tangent, maybe we'll say, is at point A. And then we've got horizontal tangents, supposedly at B and C. So the point 4, 2 is this point right here. And notice that one way that graph goes through that point, this graph goes through that point twice, one way it does not have a horizontal tangent, but the other way it does, right? By the way, if you're interested, this is the orientation on this graph. So the first time the graph goes through B, it does have a horizontal tangent. The second time it goes through B, it does not have a horizontal tangent. And then finally, point C is at 2, -2. And point C is sitting down here. Right? And that certainly is at the point 2, -2. So this all fits in really well. The graph fits in really well with the calculus that we've drawn out. Or calculated. So this is perfect. All right, so we're doing a great job here. Going through and looking at some examples of horizontal and vertical tangents. So then let's do one more problem like that. Let's do something with some trig functions in it. So let's say we have x equals 4 cosine squared theta, and y is equal to 2 sine theta. Okay, so vertical tangents. This, remember, we now know dx d theta, the parameter here is theta now, has got to be 0. So let's look at dx d theta. Be really careful here. Dx d theta, that is the chain rule, because it's the cosine squared. So this is 8 cosine theta. That's the derivative of the outside. And then times the derivative of the inside, which is negative sine theta. So dx d theta is negative 8 cosine theta sine theta. And so what do? We set that equal to 0. And so that gives me cosine theta equals 0 and sine theta equals 0. So if we're just going to look at, and I didn't really say this up here, but let's look at it just in the interval from 0 to 2 pi for theta. So cosine of theta is equal to 0 when theta is pi over 2 and 3 pi over 2. And sine of theta is equal to 0 when theta is equal to 0 and pi. Now it is really common with trig functions that you get kind of repeats between the two. In other words, you get points where both derivatives are 0. And so let's not jump the gun here. Let's go ahead and look at horizontal tangents, look at the other derivative before we go to points and all that. So for horizontal, we're looking at where dy d theta is equal to 0. Now this is simpler. Dy d theta is just 2 cosine theta. So you just set 2 cosine theta equal to 0. And you get theta is equal to pi over 2 and 3 pi over 2. So notice pi over 2 and 3 pi over 2 are in both lists. And so at theta equals pi over 2 and 3 pi over 2, both dy d theta and dx d theta both equal to 0. So we must look at the graph to see what's going on at those points. Okay? So let's see, at theta equals pi over 2, by the way, let's look at those points there. Theta equals pi over 2, x would be equal to 0, and y would be equal to 2. So you get the point 0, 2 at theta equals pi over 2. And then at theta equals 3 pi over 2, x is still 0, but y now would be negative 2. So those are the 2 points we're going to have to analyze a little bit more carefully. Now that still leaves us with theta equals 0 and theta equals pi. And so, right, because theta equals 0 and theta equals pi, we're getting vertical tangents. So at theta equals 0, x would be equal to 4, and y would be equal to 0. And theta equals pi, well, In fact, x is still 4, isn't it? Because it's cosine squared. And it's still 4, 0. So we're saying that we do have a vertical tangent at 4, 0. And at the point 0, 2 and 0, negative 2, we need to look at what's going on with the graph to see, in particular, what's going on here. So once again, let's have a look at the graph and let's see what we've got here. So go back to these problems. I'm going to enter 4. Be careful how you enter cosine squared on a calculator. You don't enter it like you write it. So be really careful there. I have to put cosine of t in parentheses, and then I'm squaring that. So be really careful there. And then y, clear that out. I have 2 sine t. Go ahead and close the parentheses. And I'm going to go ahead and go from 0 to 2 pi right here for my parameter values. Let's see what we got. Okay. So x, by the way, notice has to be positive. That makes sense in the problem. So there's our graph right there. And so, in fact, let's see. Let's go ahead and make this a little bit bigger. So if I take a picture of that, go ahead and bring that over here. And we'll make that a little bit smaller. Go ahead and paste that in there. There we go. So we have a vertical tangent at 4, 0. That makes sense. There's the point 4, 0. And certainly we've got a vertical tangent right there. And see what happens at those other points, at the point 0, 2 and 0, negative 2. And here's 0, 2 and here's 0, negative 2. What's happening is the graph comes up to that point. It's kind of like it bounces off of it. And the graph just oscillates back and forth between these 2 points. And so what would we say there based on the graph? To me, it looks like we've got horizontal tangents there. But it's kind of a, it depends on how you define that as far as whether some people would allow that to be called horizontal tangents right there. But I would say that that's what makes the most sense right there. Is what happens is the graph comes over like this, and then it literally bounces off of that point and comes back that way. So it just keeps on going back and forth like that. So kind of an unusual graph. All right. So to finish class today, I do want to, we've looked a lot at horizontal and vertical tangents. You definitely have some really good practice problems on the exam 2 review on finding horizontal and vertical tangents, given the functions are written parametrically. So let's now go on and talk about arc length. All right, so the length of a curve, don't forget, we've kind of went through a justification for this form already earlier in the semester, that if y is given as a function of x, in other words, you're given a rectangular form for a function, then the arc length is simply the integral from a to b of the square root of 1 plus dy dx quantity squared dx. Right, like that. Or in a more shortened form, you'll see it written this way, that it's the integral from a to b of ds. Right, where ds is just d arc length. And ds in this case, when it's given rectangularly, it would be the square root of 1 plus dy the square root of 1 plus dy dx squared dx. That's what ds is equal to there. All right, so we could go through, I'm not going to go through the justification here. It's really just algebra. But if x and y are given parametrically like this, then you could take the form that we have, the rectangular form above, and you could rewrite it, and it is written like this. It's the integral from t1 to t2. Those are parameter values of the square root of dx dt squared plus dy dt squared dt. And that's the parametric form for arc length right there. Okay? Now, if you recall, arc length problems could notoriously be really gross and messy problems. And this still could happen in parametric form, but it does kind of expand a little bit your ability to be able to find arc lengths, I think, in some cases. So let's say, let's work through an example. Let's say we have x equals 6t squared and y is equal to 2t cubed. And we're saying that t is in the interval from 1 to 4. And we want to find the length of the curve, right? That's what we're talking about. Find the length of the curve between those two t values. So, what are you talking about? As far as points go, when t is 1, you've got the point 6,2. And so you're talking about from the point 6,2 on the curve to the point, when t is 4, you get the point 96. And let's see, when t is 4, 4 cubed is 64 times 2 is 128. So notice we should get a relatively decent-sized number here. This curve should be relatively lengthy from the point 6,2 to 96, 128. Right? Even if it was just a straight line, it would be relatively lengthy. All right, so what do we do here? We build the pieces of our arc length integral. So dx dt is 12t, and so dx dt squared is 144t squared. dy dt is 6t squared, and so dy dt quantity squared would be 36t to the 4th. And so our arc length integral would be the integral from 1 to 4. Notice the limits of integration are t values. And this would be the square root of dx dt squared plus dy dt squared dt. And, that does simplify. There is a common factor underneath the radical of 36t squared. So you have the square root of 36t squared times 4 plus t squared dt. And so you could take the square root of 36t squared, which would be just, t's got to be positive here because of the interval we're integrating with respect to. So that's okay to write that the square root of t squared is t. So this would just be 6t times the square root of 4 plus t squared dt, like that. And, that, let's see, I'm going to continue it over here, would be the integral from 1 to 4. Let's go ahead and take that, that 6 outside of the integral, like that. And so then this would be a t here, and then this is 4 plus t squared to the 1/2 power dt. And this is just u to the 1/2 du. Because you let u be 4 plus t squared, then du would be 2t dt. So I need to multiply this integral by 2 on the inside and 1/2 on the outside, like that. And now it is exactly the power rule. But now it is just u to the 1/2 du. And so that gives me, so that's not bad. So you get s to be equal to 3, and then you're just using the power rule. So this is 4 plus t squared to the 3/2, and then a 2/3 sitting in front. And this goes from 1 to 4, like so. So the 3's divide out, that's good. So you have s is 2 times 4 plus t squared to the 3/2 from 1 to 4. And then you just put in those values. So like at 4, you get 4 plus 16 is 20. So you have S is 2 times 20 to the 3 halves, and then minus, and then the lower limit, you put in 1, and you get 5 to the 3 halves. And so that would be the exact value right there. So let's go ahead and look and see what that is on a calculator here. See if this kind of makes sense. Remember, it should be kind of a big number here. So you have 20 raised to the 1.5 power is about 89.4. So this is an approximation right here. This is about 89.4 right here. And then 5 to the 3 halves is about 11.2, approximately. So you have 89.4 minus 11.2 multiplied by 2, and you get about 156.4. And so that makes sense in the context of this problem, that it should have been a relatively lengthy length there. And so 156.4 kind of makes sense in the context of this problem. All right, so that's a nice little arc length problem to go through. Let's see, let's do one more arc length problem. And now this one is really different. You have x equals a cosine theta and y equals a sine theta. And so, let's find the length of this curve. All right, well, I'm going to find the length of the curve. Well, this is a circle with a radius equal to a. So our answer better be, the answer here better be 2 pi times the radius, or 2 pi times a when we're done. All right, that better be what we come up with to finish this problem, or to solve this problem. All right, so let's see. Let's work this out. So dx d theta would be negative a sine theta. So dx d theta squared would be a squared sine squared. And then dy d theta is a cosine theta. And so dy d theta quantity squared is a squared cosine squared theta. And so the arc length here, let's see, to go around this circle, we would need to go around this circle from 0 to 2 pi, like that. And this would be the square root of, and this would be a squared, a squared sine squared theta plus a squared cosine squared theta, d theta. And notice how nice this works out, because you have a common factor of a squared in there. So that leaves you with sine squared theta plus cosine squared theta, d theta. And then sine squared plus cosine squared is 1. Square root of a squared is a. And so notice you're quickly down to just integrating a d theta. And so that would be a theta from 0 to 2 pi. And sure enough, you get 2 pi a as the answer. Right, so it all falls out really well at the end there. All right, let's talk a minute about surface area problems. We probably won't work an example here, but we'll go through and justify the forms for surface area, and maybe we will look at an example of that next week. So with surface area, remember we're talking about rotating a curve around, and we're just going to do around the x or y axis. So if you recall from before, we've talked already about the fact that surface area was this integral, this general form for an integral, the integral from a to b of 2 pi r ds, d arc length. So in the case where y is some function of x, then this arc length formula, right, becomes, in this case, ds, we talked about already. That's the d arc length piece right there. 2 pi r is the circumference. It's the radius of rotation, right? So if y is given as a function of x, then we had this form. We had the integral from a to b of 2 pi times the radius, and it depended on the axis. So let's say y was a function of x, but the rotation was around the x-axis. Then this would be 2 pi times y times the square root of 1 plus dy dx quantity squared dx. All right, so now let's see how this changes. If you have x as a function of t and y is another function of t, so right, x and y are given parametrically, then the ds piece, the d arc length piece, we saw in the last two problems, is the square root of dx dt squared plus dy dt squared, dt. So if, let's say you've got a curve, and the rotation, and so those are we have the parametric equations for that curve, and the rotation is around the x-axis, then this is the radius right here, and that radius would be equal to y, but y is equal to g of t, right? And so the surface area integral would become this integral. The integral from t1 to t2 of 2 pi times the radius, which would be g of t, times the square root of dx dt squared plus dy dt squared, dt. Right? But if the rotation is around the y-axis, same curve, it doesn't really matter there, but around the y-axis, so here's our rotation now, then the radius is that distance right there, and that radius would be x, and x would be f of t. And so this arc length formula would be the integral from t1 to t2 of 2 pi times f of t times the square root of dx dt squared plus dy dt squared dt. Like that. So that would go with that picture right there, right? And then this integral goes with this picture right here. And I would just kind of think about what the radius is given the axis of rotation for surface area. All right, so let's go to the, let's see, so homework on next page. So you've got homework. I assigned homework at the end of Monday's lecture. And so today, homework that is due March 11th. And this is on section 7.2 of your book. You also have two problems from section 7.1. And this is problem number 68 and problem number 86. Problem 86 is a horizontal and vertical tangent line problem. Problem 68 is simply finding the equation of a tangent line, so you have to calculate a derivative. So, all right, so section 7.2, problem 68 and 86. And I also gave you two problems in section 7.1, and like I said, those are at the end of the last lecture on section 7.1. Okay, so hopefully you have a great spring break. Don't hesitate to get in touch with me. If you have any questions about anything, don't forget the homework that's due on Sunday. If I haven't got I'll get the link up for that homework to turn in the next day or two. Thank you to Jaime for reminding me last week to get that link up. So everyone have a great spring break. Get in touch with me if you have any questions. I'll also get the exam 2 review online on my Google site later tonight. Have a good week.